In this video, we're just going to start talking about three-dimensional space and review a couple of geometric concepts that you may need in the coming days. First thing, just a quick review of some geometry. What is an isosceles triangle? Well, an isosceles triangle is a triangle, I'll use some symbols here, with two equal length sides. Okay? You'll notice that kind of all of this page is kind of dealing with some geometry, but also having to do with some lengths and distances. So the next question is, how can you prove a triangle is a right triangle? Well, short of measuring something, like actually going out and measuring it, the easiest way to prove that a triangle is a right triangle is by checking, does Pythagorean theorem hold true? And by that I mean, if you take the two short sides, you're given a triangle and you measure sides, you say, well, if I take the two short sides and square them, is the sum of those two equal to the large length squared? If so, it is a right triangle. A triangle is only a right triangle if Pythagorean theorem works. And you might say, well, how is that easier than just measuring sides? Well, once we get to three-dimensional space, some of those things that used to be very easy, we need to modify how we would do that. And this is a really easy way to prove a triangle is a right triangle, regardless of how many dimensions we're looking at. Finally, find the distance between 2 points. Well, the distance formula, if you remember, I'm going to kind of just do it out here, says we do the difference between the x's and square it, and then we do the distance between the y's and square that. So of course this is -5 squared plus 9 squared. It is the square root of 106. It's really just Pythagorean theorem, okay? It's not, it's just kind of a modified version that we say, well, here are the x's. How long is this side? It's 5 units. How long is this side? This is 9 units. So one side squared plus the other side squared, and then Pythagorean theorem helps us find the distance. All right, so now talking about space. Well, let's start with this. You'll notice up here that I put this little box. This big R represents what kind of coordinate system we're talking about. If the box has a 2 in it, then we're dealing with good old X and Y, the same type of graphing we've been doing forever. If the box has a 3 in it, then we're into this, the three-dimensional space. And take a good look at this and how this graph works. You'll notice X is here and Y is here, and Z adds the height. The idea here is that what we're used to doing, the X and Y, this piece right here, it's almost as if all the time we've been doing that, we've been looking down at it. So the Z is coming off the page at us. Okay, so that's why Z has the dimension it does. Now, it's hard to draw things in three-dimensional space. So I just wanted to maybe give a little, kind of a preview of this. But it is hard to recognize how things look. But we go in this order, X, comma, Y, comma, Z. Okay. So you say, okay, X is 2. So that means we go out 2 units in the X direction. Notice I'm kind of drawing parallel to that back line. Then we go 1 unit out in the Y direction. So we're kind of right here right now. Okay, 2, 1. And then what makes it a little tricky is then we go up 3 units. So essentially, you're saying, well, I went out 2, over 1, and then up 3 units. And again, the difficult part of this is you say, well, how do you draw that? Because it ends up being somewhere like right in here that you would go out 2, over 1, and up 3. And that's hard to look at. It doesn't really look, because our paper is two-dimensional, it doesn't really look like it's in the right spot. Okay, but as difficult as it is, that is the correct way to draw. Okay. Okay, so let me do another point. Okay, so let me do -1. So actually, I'm going to have to just add a little more of an axis here. So -1, let me just draw this back. So -1, we go back 1. Okay, 2, so it means we go out 2. So again, we're kind of right here, and then we go up 5 units. So in the end, our plot is over, back 1, over 2, up 5. It's probably somewhere back here. And the reason, again, it's a little higher is because we're behind this YZ kind of plane back there. So it ends up being looking in our two-dimensional graph a little bit higher than 5. Okay, next I want to talk about y equals 3. So y equals 3 before for us would have, of course, just been in two-dimensional space a horizontal line through y equals 3. Well, this changes a little bit in three-dimensional space, and that's why it's so important to pay attention to what space we're in. In three-dimensional space, if I go to y equals 3 and I think, okay, well, what is y equals 3? I need something that goes through y equals 3. It is going to be a plane. I'm going to kind of draw it this way. I'm going to put some arrows here. And actually, it's going to go down as well. It is going to be a plane that goes through y equals 3 and is parallel to this kind of back plane here, this xz part of the graph. So it goes through y equals 3 and is a vertical plane. Okay, so the next thing, of course, is, all right, well, z equals 2. What is that going to look like? Well, z equals 2. Let me give myself a little room here. We'll go through z equals 2. Like this. And it will be a plane that is kind of like that. Okay. And again, it will continue off forever and ever in those directions. It will be a horizontal plane. So again, it will be just parallel to this kind of XY plane down here, 2 units up. Finally, I want to talk about how we would extend our distance formula and some other ideas for three-dimensional space. And the beauty is a lot of things aren't different. So finding the distance between curves, well, we still want to know how far the x's are apart. So 1 minus -3 squared plus how far the y's are apart and how far the x's are, or the z's are apart. So we've got 4 squared plus -2 squared plus -2 squared. It is the square root of 24. Okay. Next, which of the following points is closest to the xy plane? So this is like saying, okay, of those 2 points, which is closest to this kind of bottom piece right here, this kind of basic xy plane? So you think about these points. This point is x1, y is 4, and z is 2. So it goes over 1, over 4, and up 2 units. Whereas this point goes back 3, over 6, and up 4. So back 3, over 6, up 4. The one that's closest to the xy plane, of course, is the one that has the z that is closest to 0. Okay, so it's going to be 1, 4, 2. That's closest to the xy plane. Now, the next thing is the idea of projections. A projection is like saying, what if I just dropped the point or slid the point over to each plane? So let me do a sketch as rough as it will be. I've got over 1, 4, and up 2. So let's say the point is somewhere in here. Okay, so we've got 3 projections. We've got a projection on the xy plane, a projection on the yz plane, and a projection on the xz plane. So a projection again means what happens if and the reason it's called a projection is it's like saying if I shined a light on the point aimed at the XY plane, where would that shadow end up being? So think about, you've got this light and you're shining it down on the XY plane, meaning you just kind of drop the point down. Where does it end up? Of course, it would end up at 1, 4, and 0. Okay? So 1, 4, 0. Now the next one, shine the light at the YZ plane. Okay, so again, the YZ plane is back here. So it's like you have a light out here and you're shining it back. Boom. Where would that hit? Well, of course, it wouldn't have moved out in X, so it would be at 0, 4, and 2. Now at this point, if you're saying, well, is there a shortcut to this? Yes, there is. Notice that on the XY plane, Z was 0. On the YZ plane, X is 0. So I'm guessing that on the XZ plane, Y will be 0. And let's just check that. Of course, the XZ plane is over here. So imagine you've got a light. You're shining it over. Where's it going to hit? Well, you're still going to be over 1. You're still going to be up 2. But indeed, the Y will be 0. So it's going to be 1, 0, 2. Now, if you think about those points, and I can kind of sketch those in a little bit, 1, 4, 0 is here, 0, 4, 2 is maybe back in there, 1, 0, 2 is maybe up here. It says if you connected the origin to these kind of projection points, what would it end up looking like? Well, pardon my really poor sketch here. Like that, it will look like a rectangular prism. Okay. And again, the idea really is just recognizing that when those points drop down, they end up with a bunch of parallel faces. And that helps us to create this idea of a rectangular prism.